Hi, lovely people. Okay, I think the sound is working. Cool. Welcome to the live stream. Okay, this is Maths in my lounge room. You may be wondering why I have such a large whiteboard in my lounge room. Don't you? Okay, cool. Key things for today is that this is a lecture that contains everything I want to tell everybody in the course. I'm trying to make this as general as possible and answer any questions you might have about where we're up to, what we're doing, where we're going, and the maths that applies to everybody. And then that'll hopefully mean that sort of in our meeting times and in our class meetings and in the Google Meet type things, I can be spending as much time as possible helping individuals with their own problems or small groups with their own problems, because you've all seen this lecture and got a vague idea about where we're up to and the maths that we're doing. Okay? So also, just where we're up to with the course in general, this is the last week of exponentials and series and sequences and logs. Okay? The week after, week 8, we'll be going on to calculus and we'll start looking at that. So this is really the end. And as such, I'd be putting together your summary sheets, making your notes, sort of putting a new title page in your book for calculus, and just seeing this as like the end of the subject, and that we'll move on to the next part of the course. So that's happening now. Okay. What I'm going to do is go through exponential equations from the textbook, using exponentials to come up with modelling problems. So that's pretty much the way word questions are presented in this unit, and then go into a little bit of logs and how they work. Okay? So, I think the best exponential equations thing is just to get started with doing them. Okay? So if you look at exercise 11.07, okay, in the Nelson textbook, okay, question 1C is a good illustration of the thought behind that. So 1C, okay, and what you're doing is you're solving exponential equations without the use of logs. Okay, logs sometimes give you a decimal approximation. It's very easy to get a decimal approximation of this stuff with logs, but sometimes you want it more exact, and then it helps to phrase it as an exponential equation. So you've got the question 4 to the 2x minus 1. Minus 32 equals 0. Okay, now this is an equation. We do the same thing to both sides. Happy days. Okay, so what I'm going to do is 4 to the 2x minus 1 equals 32. Taking 32 from both sides. This can be written as 2 to the 2 times 2x, minus 1 equals 2 to the 5. And my job here was to get both bases the same. So 2 is the smallest base of 4. Like 4 is 2 squared. So I can write that 4 as 2 squared inside brackets. And then 32 is 2 to the 5. Okay? And so now I've got them both with 2 on the base. So I can just ignore the bases and set these equations as equal to each other. But remember the rule of index notation, that you can times these together. So he ends up being 2 to the 2 outside of 2x minus 1. Okay, which equals 2 to the 5. Okay, both of these can be doofed in one step. 2 to some stuff equals 2 to some stuff. Okay, so all we've got to do is equate make the tops equal, okay? And we can dwarf the bottom because it's all to the power of stuff and it's all the same. So we end up with, I'll expand that 2 while I'm here, 4x minus 2, because 2 times 2, 2 times minus 1, equals 5. And then add 2 to both sides, and I end up with 4x equals 7, therefore x equals 7 on 4. Okay, now if you equate that up here, 7 on 4, times it by 2, so you'll get 7 on 2, minus 1, and then you put that into your calculator, it should work. Okay, and it should all hang together as a package. Okay? Usually they give you ones which give you whole number answers and not fractions at the start, but welcome to spec methods. Okay? Cool. Okay, the next one we'll do, okay, will be 2e from the same set, which goes 6 to the x minus 1 minus 16 equals 20. Okay, a little bit of strategy to work with these helps. If I were you and you're watching it sort of in the video form, I'd give that one a go. Okay, see if you can get there, then jump ahead to when I show you the answer and check that you're right. And if you can't, sort of do it with me. Okay? Well, should probably stand on this side wall. I'm getting in the way of the camera. Well, if you've got any questions and you're on the live stream, just ask them now. I'll look for questions. Nobody's asking a question. That's all cool. Okay. I'd add 16 to both sides. Then 36 is 6 squared, so this is quite nice. And then doof the bases. And we're done. Okay? And that's the sort of the thinking behind exponential equations. I'll let you guys have a play with that. Okay, if you've got any questions, please ask in the tutorial session or on the live stream comment thing. Okay. Next we'll move on with exercise 11.08. Okay, it's all about using exponential equations to model real life situations. Okay, so if you go to question 11.08, sorry, exercise 11.08 in the Nelson, and you go to question 2, you'll see that it gives you this equation. Okay, it gives you that equation, and then it says, what's your initial value and your growth factor? Okay, and it's just aligning those two ideas. what's your initial value, and what's your growth factor. Okay, now this is your classic model using an exponential equation. Okay, and it's key to understanding this is that this is your growth factor. Because as you add 1 to t, this is the number that times in by itself, and by itself, and by itself, and by itself, okay, over and over again. It's him, because it's to the power of t. Your initial value is him. Because when t is 0 at the start, the initiation, the initial part, this is 1, because anything to the 0 is 1, you're left with 1 times him. Okay, and that's how the sort of thing works together as a little bit of a package and a whole. Okay? Hopefully that made sense. Any questions, queries, problems? Look and see if there's any comments. No comments? No questions? Cool. Okay. Move on to the next thing. The next one. Oh, that's horrible. I should clean my whiteboard. It's in my house. That's really bad if you can't keep your whiteboard clean in your own house. Don't have English coming and spoiling stuff. If you go to question 3A in the same set, you'll see a problem that goes on an algal bloom, okay? And it uses an algal bloom as an example of exponential growth. And it's a great example of exponential growth because the bigger the algal bloom, the faster it's going to grow. That's what an exponential does. Okay, the bigger the initial value, the bigger the thing, you take him and you times him by the growth. Okay, and it's growing by the same rate, no matter how big it is at the start or at the end. Exponential growth. Okay, and so sort of the key with that is that your initial value in the thing is 3 meters squared. Now this is just a unit, so it's not part of the growth, and then it's growing at 5% per unit of time. Okay, so we times that 3 meters squared by 1.05, okay, to the power of t, however many units of time. Okay, and this is like your 5%, your 1 whole plus your 5%. Okay, and it's times by itself for every unit of time. So we go, one question it asks, what is it after 20, I think it's days. Okay, 20 days, and you just plug that into your calculator, resolve it. Okay, I didn't write the answer here. My guess is that it's going to be about 8 meters square, but you can check that on your calculator. Okay, any questions, queries, or problems about that? Nope. Okay then. Cool. Next. Okay, next we're moving on to logs. I would do one of the exercises on logs that's in there. The worksheets on logs are really good. The textbook stuff I put on logs are really good. And they just give you a background in logs and how they work. Okay, just to recap the stuff that we were talking about with logs when we were in class. Okay, you have a log. Yeah, and it's a way of rephrasing a question you already can do. Okay, so you have your 5 to the power of 3, which equals 125. Okay, that makes the answer, the 125, the value you have for that exponential as the subject of the equation or the subject of the statement. Okay, then you can rearrange that. The third root of 125 is what? And that's 5. Okay, now logs help you rearrange this to make 3 what you're trying to find. Okay, and so the log 5 125 equals 3. And that's what the log does. It goes and makes the thing we're trying to find the subject of the equality. Okay, that's the key value that logs do. Okay, and they follow the same rules of index laws, just like the rest. So if you want to do the multiplication one, okay, and say you've got something like 10 to the 3 times 10 to the 2, that's going to equal 10 to the 5. Okay, or 1,000 times 100 equals 100,000. Okay, in logs, we'd write that log 1,000 times log 100 equals log 100,000. Okay? Now notice that this is the same statement as that. But what this is saying log 1,000 is 3 zeros. So here's 3. This value here is the same as 3. This value here is the same as 2. And this value here is the same as 5. So notice the pattern. If you times these two things together here, you add them here. Okay? The times in the log form, adding the log form is timesing. Okay? So you can, there should have written here a plus to begin with. Okay? Plus on this side means times on that side. I'm sorry about that. Okay? Plus in the middle is times in there. Because this is the value of the log. And it makes 5. And you can see that the number that's in this position, you can times them together and get the answer here. So what this should show, if I could say it properly, is that log A plus log B equals log A times B. This is the point I'm trying to make. The stuff in the brackets if you times it together, you add the logs. Okay? Hopefully that's clear. Another thing that I may have forgotten to mention is that when you don't write a base, you assume it's 10. Okay, this is an engineering thing. When there's no base on the logs, you assume that it's 10. Okay? Hopefully that made sense to people. I'll just see if there's any questions in the comments. I wonder if people can use the comments. I have to email and check around for that. Cool. Okay. That's multiplication. Obviously, there's a division one too. That's a reverse. So where I've got plus on this side, I've got take away. I've got plus with the multiplication one. I'm going to write take away and divide with the division one. So if you've got 10 to the 5 divided by 10 to the 3, that equals 10 to the 2. Okay? Or 1 and 5 zeros, so 100,000 divided by 100 equals 1,000. Okay, and then log 100,000 or your 5 minus log 100 or your 2 should equal log, I put an extra 0 there, that's weird, log 1,000. Okay, and its rule can be written as log A minus log B equals log A on B. Okay, and with this one, it's just good to pay attention. When it's a minus here, it's on the bottom of the divide. Okay, when it's a plus here, it's on top of the divide. Minus on the bottom of the divide. Okay, so yeah, when it's plus, you times them. When it's minus, you divide them, and you put the negative thing on the bottom. Negative, bottom, negative, bottom. Hopefully that makes sense. Makes sense to me. If it's confusing for you guys, I'm sorry. Okay. And if you've got any questions, please ask. Okay. We've had a plus one. We've had a minus one. Now we'll do a powers of powers one, because these things generally follow that pattern. Okay. Powers of powers go along the lines of 10 to the 2 to the power of 3 equals 10 to the 6. Okay, we know that because that's like 100 times itself 3 times. I'm not going to write out all the zeros because I want some space on the board for one more thing. Okay, but like this is 100 to the power of 3, so it's 100 times 100 times 100. You can times these ones together and chuck the 6 there. Okay, that's the index power of power property. Okay, with logarithms, this is a really useful technique. Okay, this is incredibly useful, yeah? If you have log, okay, and it's base 10, and you've got 10 to the 2 to the power of 3. Okay? If you've got two things in this little index position here and multiply together, or anything in this index position here and it's multiplied together, you can pull it out and times it by the log. Okay? So here's going to be log 2 times log 2 times 10 to the 3. Okay? And the reason for this, like I might make it a bit more obvious. Sorry, I'm not used to talking to a camera and not a person. Freaks me out. This is because log 10 to the 2 all equals 2. How many times do you times 10 by itself to get to 10 to the 2? Obviously 2 times. So all of him is 2. Yeah? Now this is obviously, this index position can be times by 3. So we can times it all by 3. Okay? And 2 by 3 is 6. Yeah? Just as 2 times 3 is 6 here, how many times do you times 10 by itself to get to like 10 to the 6? 6 times. Okay? In fact, you can bring them both out. So you can have 6 equals log base 10 to the 10 to the 6, and you can also have because this is to the 1, so this is 1, and you're timesing it by 6. So the point I'm making really, really poorly is that whatever is up here in your log position, you can times by the front. If you've got something with an index up here, you can just get rid of him and put him out the front if that makes the question easier to solve. Okay? Because the log is a count of how many times it's times by itself. So you can get this one over there. Okay? The other rule, so this rule can be written as log a to the b equals b log a. So you can take the thing from the index position and times them out the front. And that'll work for all bases as long as it's consistent. Okay? Cool. I'll write up the change of baseline. Okay? It's a bit of an obscure one, but because most of your things you're doing is calculators, it actually becomes really useful because most calculators only have one log table in them, and so to answer questions you need to be able to change the base of the log to a different base. Okay? So if you've got, this is a change of base rule. And it states if you have log base A, B, that'll equal log C to the B over log C to the A. Okay, this equation will equal that one. Sorry, this side of the equation will equal that one. Now notice that B and A, so your base, is B and A, B and A, and that C's the same. Okay, C needs to be the same to make him work. So if you've got log 10 to the 1000. Okay, and for some reason your calculator doesn't do log 10, you can just go log E, and log E is the ln button on most calculators, to the 1000, and divide it by log E or ln to the 10, and you should get the answer 3. Okay? So that's the log laws. I'm going to write them up on the board and then just sort of, so you can copy them down if you want, although they're all over the internet, so I might not even do that. That's cool. That's your log laws. Those are your log properties. That's the stuff on exponentials that I wanted to finish off of, and exponential properties. I would get through as much of the week 7 work as you can. Okay, do practice these. They look easy when I do them. Okay, I've done before, but they can be tricky, and there's a whole bunch of things where it's like, oh, what was the rule again? And which rule do I use? And that practice will make you more combat efficient with that. Okay, but I'll end the live stream there. If there's any questions, queries, or problems. Cool. Okay. Oh, well, I will say goodbye, and hopefully I can see you in person too, because yeah, this doesn't really suit my teaching style. Okay, bye guys.